Hello, everybody. Thanks again for joining us for another Technical Sessions webinar. We've had a time change because we were supposed to be meeting in Polo's Social Lounge, but there's a lot going on right now with COVID-19. So new restrictions came in Alberta, and which means that we can't meet in person. So we're back online, and unfortunately for a lot of you, this time is not very convenient, but thank you for the ones that were able to join us. And of course, some of you are going to watch this recording, so thank you for doing that as well. So today we've got a really great presentation from HOERBIGER about capacity control, reciprocating compressors. Before we start, I'm going to have Muammer and Javid give a little intro about HOERBIGER and in Canada as well, their local presence here. So take it away.
Thank you. Thanks very much, Andrew. Hello, ladies and gentlemen. My name is Muammer Kosar, and I'm leading the sales group in HOERBIGER Canada. Talking about the HOERBIGER, the journey begins in 1895 with Hans HOERBIGER in Vienna, Austria, with his invention of seal plate valve for compressors. And for Canada, like in 1972, when HOERBIGER opens its shop in Mississauga, Ontario. And globally, by 1997, HOERBIGER becomes a group holding company in Switzerland. In compression technology, we design and manufacture valves and valve systems, rings and packings and lubrication systems, control systems, and also valve actuators and piezo valves. Currently, we serve our customers with our 6,000 employees in 128 locations and in 48 different countries in the world. Coming to Canada, we have 2 locations to serve the West. We have a service center in Edmonton, located at 50th Street. And to serve the East of Canada, we have a service center in Mississauga. Javid, our sales support customer service manager, so he will just mention a little bit details of what we do in these locations. Javid?
Thanks, Muammer, and good afternoon, everyone. As Muammer said, we have 2 service facilities in Canada, one in Western Canada in Edmonton, in Alberta, one in Mississauga. In Edmonton, we have a full service branch. We are doing valve refurbishment, including leak testing and crack detection. We also undertake packing refurbishment. Again, we do leak testing of the packings. We do manufacture piston rings, and we do piston rod inspections and refurbishment of piston rods up to 5-inch rods. We do con rod and crosshead inspection and refurbishment. We have about 25 hydrocom installations around Canada, so we also have a hydrocom actuator service and testing facility in Edmonton. This includes hydraulic and electric function test of the actuator. For the industrial gas customers, especially for customers having oxygen compressors, we have an O2 clean room where we do all of our O2 valve service. As you all would probably appreciate that O2 doesn't require any oil, so it has to be a very clean type of a room with specifications. We also have a rapid response cell to manufacture seats, guards, and valve plates on CNC machines. Additionally, we have a well-stocked inventory of valve components, including raw materials to produce seats, guards, and thermoplastic, as well as peak valve plates. In our Edmonton shop, we have lifting capabilities of 5-ton and 3-ton cranes, 2 cranes, overhead cranes in 2 well-spaced bays. Mississauga branch will have similar capabilities, and we have revamped, and it will be opening up and be fully functional in about 2 to 3 weeks. Thank you very much.
Here, maybe I should add one more thing, Andrew. which is quite important. Travis says there are more than 30 hydrocom capacity control systems across Canada, controlling very critical compressors in the process plants. And there are more than 400 hydrocom actuators working continuously, 7/24. We service them from Edmonton, and we exchange them at both of our locations. Thank you.
Excellent. Jared, can you introduce our speaker for today?
You betcha. Yeah, so appreciate you guys taking the time. And our speaker today is John Ladd, and he is the engineering manager at HOERBIGER Service Inc. based in Houston, Texas. He supports the North American service branches, providing repairs and upgrades on reciprocating compressors for the oil and gas and chemical, as well as petrochemical industries. Prior to his current role, he was the Solutions REE Engineering Specialist and Compressor Analyst at HOERBIGER Service Inc. John earned his master's in mechanical engineering at Colorado State University with a focus on legacy integral pipeline compressors. So with that, I'll pass it over to John to take it away. Thanks, John.
All right. Well, Jared, thank you very much. Let's see. All right. Is my screen coming through?
Yep, you can see the screen, just full screen, and there you go.
Perfect. Well, good evening, everyone, and thank you for dialing in. I know it's the dinner hour or approaching the dinner hour for most of y'all, so we greatly appreciate y'all coming here to learn a little bit about capacity control of reciprocating compressors. So throughout this presentation, we have several natural breaks in it. So if you have any questions along the way, please put them in the chat box, and we would be happy to address those when we get to those at natural break. So to kick off the presentation, just to recap for why we need capacity control on compressors and some of the working theory behind how they actually move gas. So as we all know, reciprocating compressors are positive displacement machines, meaning they will move as much gas as you feed them. And oftentimes the downstream process doesn't require the full capacity of the compressors, so we need a means to turn it down or regulate the amount of flow going to it. Some additional reasons that we need capacity control on compressors is sometimes we want to save energy. Sometimes we want to prevent the driver from exceeding its power limit. This is fairly common in the midstream side of the industry. Then if your suction pressure and your discharge pressures are changing, then obviously your interstage pressures will change, and you need some form of capacity control to keep everything balanced. If you have side streams in your process, very similar to the reason as needing to balance your interstage pressures. And then it's also very common in midstream is you want to keep your driver torque within a fixed band. This is of particular importance when you have a natural gas driver, and they perform best when they are in their ideal torque band. So throughout this presentation, we'll go over some things that you should consider over the various capacity control methods. So that's the ability to actually turn down the compressor, how much turn down you need, how easy it is to automate a certain type of capacity control, how quickly do you need it to respond, and then what are the reliability impacts of implementing such a system, whether it's heating, the rod loads, the valves, are there any acoustical issues, are there any torsional issues? And then we obviously want a system that is able to do everything we need, but we also don't want it to break the bank. So we have this slide here just to go over how the mass flow of a compressor is calculated. So these are the 4 knobs that we can turn if we want to adjust the flow rate through a cylinder. So the first knob that we can turn is adjusting the speed of the compressor. So if you speed it up, you're obviously going to pump more gas. If you slow it down, you'll pump less gas. Then the next term we have is the suction gas density. So this is directly proportional to your suction gas pressure. If you have greater suction gas density, it means you have more molecules in the same amount of space. And because these are positive displacement machines, it's going to move those molecules down the line. Then next, you have your swept volume. So this is your bore area times your stroke. And then finally, we have this last term, which is the volumetric efficiency term. So all this term means is it is the percentage of the stroke that your suction valves are open. So for this particular PV card we are seeing here, so between V2 and V1, that is 100% of your stroke. And from B to C, that is your volumetric efficiency. So for this example curve, we're probably looking at 80 to 85% volumetric efficiency. And this term is calculated by these parameters down here. So it is your clearance volume, your compression ratio, and your kappa, also known as the isentropic exponent. All right. So as we had touched on the first slide, so one of the reasons for the need for capacity control is we want to make sure our drivers remain within their power limit. And this is the formula that we use to calculate the required power. So the area inside the PV curve is the work being done on the gas. And then this equation here just converts that work into a rate. And then once we have the rate of work being done, we are then able to get the power demand. So P, that's the area within the PV card. L is the length of your stroke. A is your piston area. So the L in the A term is your swept volume. And N is your compressor speed. And then this 33,000 is just a constant, and that gets all these funny units to agree with each other. Within the world of reciprocating compressor capacity control, there are two main families. There is stepwise control and stepless capacity control. So by stepwise, we mean that you have individual load steps. The fewest number of load steps you can have is 2, meaning your compressor can be on or it can be all the way off. And then up from 2, you can have 3, 4, 5, and upwards of 48, if not more, individual load steps. It just depends on how many actuation devices you want to put on your compressor, how many cylinders you have, and the amount of complexity that you are willing to tolerate on your compressor. And the other family of capacity control is a stepless capacity control. So by stepless, we mean it has an infinite range of capacities. So meaning if your downstream process needs 62.5% of the compressor's flow rate, it will be able to deliver exactly that amount to the downstream process. And there are a number of different methods out there to have a stepwise and a stepless capacity control system. All right, so since we changed this to a virtual presentation, we threw a couple quiz topics in here. These are just to get y'all's feedback and to stir up some conversation.
No, unfortunately, GoToWebinar doesn't give us that many options. We can only have 5.
Oh.
So we've truncated the options, but anyways, you can select from here. So I'll give everybody a few chances or a few minutes or a few seconds to select your choices, and then we'll see the results.
Awesome.
Okay. All right, let's, for the sake of time, let's just close that off here. There's a couple more votes coming in. 3, 2, 1. Okay, let's take a look here. So 0% on the start and stop, 25% suction throttling, 25% variable stroke, 13% recycling, and 38% said all of the above are capacity control methods.
All right. Well, so the correct answer was there's no such thing as a variable stroke compressor. So the reason for that is the crankshaft is what controls the stroke, and then while the compressor is running, that crankshaft has fixed geometry, so we aren't able to adjust the flow through it. And then throughout the presentation, we'll go over start-stop control, the recycle control, how suction throttling actually works, how you can add or reduce the clearance volume in a cylinder, go over the principles for how reverse flow actuation works, go over cylinder end deactivation and speed control. And so then we put all these 8 methods on this chart here, just showing the 4 parameters that you should consider whenever implementing a capacity control system. So these 4 parameters are the stability of that capacity control system, how much turndown it has, the complexity of implementing such a system, and the efficiency of that system. So to start it off, we'll take a look at the start-stop control. So we see that it has a very low stability. So if you have a 2,000 horsepower compressor and you are starting and stopping it, that will introduce quite a shock to the system. So you'll either pull down your header or you'll pressure up your downstream headers, just the fact of bringing that compressor online and offline. So the start-stop does have fantastic turndown capabilities. I mean, honestly, you can go from full load to 0 load, but there's no intermediate steps. It's very low on the complexity thing. You just need the ability to start and stop the compressor with ease. And then from an efficiency standpoint, when the compressor is offline, it's obviously not consuming any power. Then next is the recycling method. Some people call this the kickback method, the recirc valves, the spillback valve. There's all sorts of names for it. So it's a very stable system. It is a stepless capacity control method. It can have up to 100% turn down. It's not very complex, but the downside is a recycle valve is not very efficient. Then for a suction throttle valve, it's comparable to a recycle valve in the stability and the simplicity of implementing the system, but its downside, it has limited turn down and limited efficiency. And for the clearance volume term, it's in the middle of the pack for all 3, except it is an extremely efficient means to reduce the capacity of the compressor. The reverse flow actuation type of device. So this is what we call our hydrocom system. So it's extremely stable. It has a complete turn down range, meaning you go from full load to 0 load. The one downside is it is a fairly complex system, but it is very efficient. And then same story for end deactivation and the speed control. All right. So first we will cover the external methods of capacity control for these compressors. So the first method is the spillback control or the recycle control. So what this means is that the compressor is at a fixed geometry, meaning it's always going to pump the same amount of gas regardless of what the downstream process needs. So if your downstream process only needs 50% of the compressor's flow rate, it means that 50% of the gas that has been compressed is going to go back through this recycle valve, go back to the suction side, and get recompressed again and again and again and again. So as we can see by the simple process flow diagram, it's a very simple system, but it is a very inefficient system because you are continuously doing 100% of the work, regardless how much gas the downstream process needs. So if there are any power limitations on the compressor, the spillback valve is not the type of capacity control that can help reduce the power demand effectively. Then next is the suction valve throttling method. So this is where you allow your suction pressure to increase or decrease depending on the flow demand. So if you drop your suction gas pressure, your suction gas density will decrease, which we are seeing on this red curve. By decreasing our suction gas density, we are reducing the amount of molecules that are being pulled into the cylinder. And then the second term that we are affecting in our mass flow equation is we are reducing the volumetric efficiency as well. So we see on the blue curve, we're probably sitting at an 85% BE. Then on the red curve, we are sitting at probably a 75% BE. So that is another indication that we are pulling less gas into the cylinder. We actually do end up saving a little bit of power doing this, but it is not the most efficient means to reduce the capacity. The other drawback of using a suction valve throttle is that you increase your compression ratio. And if you increase your compression ratio, then your discharge temperature will also increase. All right. So in the downstream world, we don't see very much speed control on reciprocating compressors. Most of these units use a synchronous fixed speed electric motor. So it's whether it's running at 277 RPM, 300 RPM, 327, 450, whatever that motor is rated for, it's going to continue to spin at that speed, regardless of what the compressor needs. There are a handful of installations that use a VFD drive. These are very efficient, but the downside of using them is they are extremely expensive and they take up a lot of space. In the midstream side of the world, it is very common for compressors to be driven by a gas engine. These gas engines have a speed range, typically plus minus 20% of their average speed. So that means you can adjust your capacity by that amount. The downside of using a variable speed to control the capacity is you may introduce or you may excite a torsional natural frequency in the compressor itself. So oftentimes there are dead bands, meaning you can't run at a certain speed. You have to pass through that band extremely quickly. So it's pseudo stepless. So it's stepless to a point, and then it has to step across that. Then it goes back to a stepless control. It does wreak havoc on the valve design. So valves are sprung for a particular operating condition, gas composition, and speed. And if we are changing those parameters drastically, then the valve dynamics won't be ideal anymore. So here is an extreme example of a valve that was sprung for a high speed, but when the speed was dropped to 750 RPM, the valve became oversprung, resulting in excessive amount of valve flutter. All right. And so those are the three methods of external capacity control on compressors. If you all have any questions about these systems, please put them in the chat, and we would be happy to address those at the next natural stopping point. So now we will dive into the capacity control methods that are a part of the compressor itself. So the first one is looking at cylinder end deactivation. So we threw a the quiz in here, just get an idea of what type of cylinder deactivation y'all's compressors use. Whether it's a plug unloader, a suction valve unloader, whether it's finger or a needle style. Do you remove the valves when you know you're not going to need capacity for a long period of time? Do you have port unloaders, or do you use a combination of all four of these?
Oh, sorry about that. I'm got to get on the ball here. Oh, thanks. Okay, so what kind of cylinder deactivation does your compressor use? Please select one. Plug unloader, suction valve unloader, finger or needle, valve removal, port unloader, or combination. We've got a good number of people who voted so far. If there aren't any more in the next couple of seconds, I'll shut it down. Okay. So nobody's using plug unloaders, at least on this call anyways.
All right.
Suction valve unloaders, 56%. Nobody's voted on valve removal or port unloader, and 44% are using a combination. So I'd be curious to know what the combination you guys are using, and feel free to put that in the chat as well. Okay, thank you.
Great. Let's move that out of the way. Okay, so now let's dive into the different methods to deactivate the cylinder. So the most common methods out there is to use a plug or a port unloader. So these terms are often used interchangeably, but they use the same principle. So when the plug is down, it seals this hole, which then prevents gas from flowing back into the suction plenum, allowing the natural compression process to start. When you have a suction valve with a finger unloader, this is what a typical assembly will look like. You have your actuator on top, bolts onto your valve cover. The cover then pushes on the cage, which then holds the valve in place. And then this actuator then has air pressure on top, and then pushes on top of the finger, holding the suction valve in the fully open position. And then here is a snip of a partial valve with a plug unloader. So by a partial valve, I mean we have the center of the valve open. That allows the plug to seat on it, sealing the gas inside the chamber, allowing compression to start. Then when the plug is retracted, that port is open, allowing gas to flow freely in and out of the cylinder. So the main benefits of these systems, they're pretty simple to put on a compressor. They're an efficient means of reducing the capacity, and depending on the control scheme, they can react extremely quickly. The downside of these systems is they are stepwise, so meaning they are fully loaded or fully unloaded. They can interfere with the maintenance on a compressor. It's hard to get these plugs to be aligned, keeping those surfaces trued up. Putting a finger on a valve it's another maintenance item. There are some parasitic losses of the gas shuttling back and forth across that restriction. And then, so it's usually done on the head end side of the cylinder, but it is also very common to have it on the crank end side to assist with the start and stop of the compressor. All right. And so if you have a suction valve with a finger unloader on it, here are some of the design considerations that need to be taken into account. So we would need to know the exact operating conditions for that particular compressor, because that will dictate how much backflow force is going across the valve trying to close it. Because as gas flows from inside the cylinder back to the plenum. There is drag force on the plate or ring or poppet trying to close it, and then your finger or needle assembly is needed to help hold it shut. And then all that back force often tries to bend the plate or the ring or the bullet, and we just need to make sure that the sealing element is strong enough to handle that back force. And then we also need to ensure that the fingers are strong enough to be able to hold it down and not be at risk of damage. All right. So within the world of actuators, there are several different styles out there. So on the left-hand side is a stacked piston actuator. So the air is delivered on top of this actuator. The air then pushes on top of these pistons, which then pushes the rod down, pushing the finger, holding the finger in the fully open position. So this is what we call an air to unload style of actuator. Then next there is a diaphragm style. So very, very similar in working principle to the piston. You have air delivered on top. It then works and then pressurizes the diaphragm, pushing the rod down, putting the valve in the unload position. Next is a reverse acting style of actuator to be used on suction valves with finger unloader, except it uses a spring force to hold the valve in the fully open position. And then you deliver air on the backside to then counteract that spring force, allowing the suction valve to open and close as a normal suction valve. And then here is a snip of a typical example of a plug and loader. So where you deliver air on top, air then presses on the piston then connects to the rod, then the rod then holds the plug down in the loaded position. So this drawing here is actually the top end of this plug and loader here. The air pushes down and holds the plug in place, allowing the normal compression process to start. All right. And for the different types of unloaders out there, so you have your plug and loader. It can be used on plug, ring, and poppet valves. Here's your finger style unloader used on plate and ring styles. Here's your pin or needle style that's solely used on poppet valves. And then this unique contraption is a radial poppet valve unloader. Although these do work, they do become a maintenance headache because it is very difficult to get these poppets to be clocked in the correct position. And so they are very prone to leakage, and it's a giant chunk of metal to be putting in and pulling out of a compressor. So some of the design considerations, I won't read these for you since y'all will have this presentation for y'all's records. But the key takeaway is you just want to make sure that the material you choose, your unloading device, is suitable for the gas that it will be operating in. And we want to make sure that it is designed with adequate strength, so that way we don't see any premature failures. All right. So these are the different types of reverse flow control actuators out there. So this is a hydraulic system. This is an electric system. So it works on the principle of electromagnets. Then here is a hydraulic system. And then here is another hydraulic system. So these two in the middle are both the HOERBIGER products. So this is the eHydrocom system. So it's got two banks of electromagnets in it that you put a high voltage to. That voltage then pulls on two magnetic plates, and it works on the same principle as the traditional hydraulic version, which regulates the opening and closing of the suction valves. So we have this chart here going over how it works, but I figure it's way easier to see how it actually works with an animation. So this is how the hydraulic system works. So right now the compressor is at full load. So here we are at top dead center. So and then once you are at top dead center, you start backstroke. So you're starting the re-expansion process. Then your suction valves open. You are pulling gas into the chamber, and you pull gas into the chamber until bottom dead center. This is where your suction valves close, and then you restart the compression process. And once you hit this point, your discharge valves open and flow starts moving down the line. So how this reverse flow actuation device works, it actually controls when the suction valve will close. So once again, we'll start at top dead center, follows the same re-expansion path, follows the same intake path where you get to bottom dead center, except we see that there is hydraulic pressure being delivered to the top of the actuator, holding the suction valve in the open position, allowing gas to escape back into the suction plenum. It then does that until a prescribed time where the hydraulic pressure is released, allowing the suction valve to close, and then the compression process begins, and then you have a reduced quantity of gas being discharged. And then this happens every single cycle of the compressor, allowing you to finely tune the capacity of the unit. All right. So before going on to the typical unloading problems we see, are there any questions about cylinder end deactivation?
Well, we don't see any questions come in at all, but that animation was amazing. Though I've honestly never really seen the operation of the hydrocom, and that just was great. So yeah, if there's no questions throughout the presentation, I mean, you know, definitely interested in getting them for the end of the presentation. So just keep your thinking caps on. So we got a poll coming up soon. Oh, here we do.
All right, and here's one more poll.
What are the common unloader problems? Select all that apply. Plug/valve leaking, getting stuck in loaded or unloaded position, component failures. This is a multiple answer, multiple choice. All right. Thanks, everybody. We'll shut that down. And so let's see what the percentages are. 80% plug and valve leaking, 60% getting stuck in loaded, unloaded position, and 70% component failures.
All right, perfect. Well, thank you very much, everyone. All right, it's very common to see all three of those. That was more just to gauge what the biggest pain point are on your on-off unloading systems. So whether it is a plug and loader or a finger unloader, it's very common to suffer from insufficient actuation pressure. So meaning there is not enough air to keep the finger or the plug in the down position. So when this happens, when the gas is backflowing across the finger, it is overpowering the available unloading force, causing the finger to lift up, and then it gets a little bit of pressure, it closes down, opens up, closes down, opens up, closes down. And then by doing that, you will often see damage on the fingers themselves, the plates, rings. If this is happening on a plug and loader, you'll see a lot of wear on the plug as well as the plug seat. And then you may see some damage on the top of the unloader rod or on top of the finger unloader assembly. All right. So here is an extreme example where the plant had an ample amount of plant air. And then in doing so, they were putting an excessive amount of air pressure on the finger unloaders. So I can't remember exactly, but for this case, they were putting like 200, 250 PSI of shop air on the unloading actuator. And these unloading actuators are typically designed for 70 to 100 PSI. So they were dramatically exceeding the design factors, and we can see damage on the plates themselves where the fingers will indent into the softer plastic plate material. If the unloading force is truly excessive, you may buckle the fingers and they will snap off like that, or you may see some damage on these loading caps as well. All right, so this is of a particular concern with a finger unloader or a needle unloader, is you want all your fingers or your needles to be on the same plane, meaning you don't want your unloader caught in the valve or with one leg longer than the other, because that longest leg will be the one that presses hardest on the valve. And so then that side of the valve will see the most unloading force, and then the other side of the plate or ring will flutter back and forth. In doing that, it can damage the plate or ring, or it can also damage the shorter fingers because that side of the plate is continuously whipping back and forth and impacting on it. Then here is an example of if you don't have a quick exhaust valve on the unloading actuators. So meaning it is trapping that supply air inside the actuator and it's leaking out very slowly. In doing so, the unloader cap or the unloader rod is retracting very slowly, and then it's often getting beat up along the way, and you'll see indentation on your caps like this. You'll see damage on your plug seats. All sorts of problems can be tied back to slow extension or retraction of the actuators. Here is an extreme example of a plug that has been heavily excuse me, got something stuck in my throat. A plug that has been heavily left in the field. This is surprisingly common to see because these are heavy devices to pull on and off the compressor. They're often left on the deck while the valves, pistons, and packing are sent to the repair facility, so they don't get a lot of love and attention. So as these plugs and plug seats get damaged, you introduce a leak path, and then this leak path can result in a dramatic increase in the discharge temperature on the compressor. So even a tiny effective flow area leakage, so we're talking about 0.1 square centimeters. So if you hold your 4 fingers together and form that little square in there, that's about 0.1 square centimeters. So that little amount of leakage can result in greater than 10 degrees of discharge temperature increase when you have a high cap of gas. So that's typically a gas with a lot of H2 in it. It's fairly common with nitrogen in it as well. Then a common complaint that we hear from end users is that they experience elevated temperatures when they are running unloaded for a prolonged period of time. This is just a theory that explains why that is. So when you throttle in ideal gas, it is an Icin isothermal process. So meaning you don't have any change in temperature, which is represented by these red lines. So you have higher pressure to enter the cylinder. So it's isothermally throttling across the valve or the plug. But the compression process is an isentropic process, which then follows a different line, which are these blue lines. So when you are compressing the gas, it is exceeding the pressure in the plenum. So the temperature is heating up a little bit. Then that slightly hotter gas is then pulled back across that suction valve or that plug opening. And then that compression process starts again, which heats up the gas further. And then this process continues and continues and continues until you reach a steady state process, typically where there is enough heat being taken away by the other side of the cylinder, or it's cooling off, or it's being conducted into the cylinder body itself. All right. So then going back to that extreme example of damage on a plug, there are several wear parts in these actuators that do need to be serviced on a regular basis. There are seals down on these rods you see on both styles of actuators out there. These seals need to be serviced to reduce the amount of process gas leakage, either going up into the actuator or leaking out onto the compressor deck. There are seals on these pistons, and we need to ensure that these piston seals are in good working order. Otherwise, you'll get blow-by across them, and then your actuator won't function as it should. Then if these actuators have been just thrown on a deck and the rods get damaged, it's possible for them to get bound up, which could contribute to them getting stuck in the loaded or the unloaded position. If you have a dirty gas, it's very common for that sticky gas to work its way into these little cracks and crevices. And then in doing so, it's very common for these to get stuck in the up or the down position. And then the same can be true for this style of actuator as well. All right. Then here are some unique methods for cylinder end deactivation. This is one where you actually have a plug valve that plumbs into the head end of the cylinder and then recirculates it back to the pulsation bottle. This system is extremely efficient, but as you can imagine, it's very costly to implement such a system like this. And then if you know that your compressor is only going to need 50% of its capacity for an extended period of time, it's fairly common to just remove the head end suction valve, which does the same thing as a cylinder end deactivation, except you have less suction gas throttling going back and forth, so then you experience less heating. All right. And for the clearance volume control, so this is where you add or reduce the amount of dead volume at top dead center in the process. So you can do that either by having a fixed volume pocket or a variable volume clearance pocket. Then this slide here just goes over impact of adding clearance volume to different compression ratio processes. So we see if you have a low compression ratio, it will have a relatively low impact or a low amount of turn down at reducing the capacity. So for this example, it's a compression ratio of 1.5. When you add 15% additional clearance volume, you're only reducing the capacity by 6%. But if you add the same amount of clearance volume to a higher compression ratio, 2.5, that amount of turn down jumps to 12%. And so then that all just relates back to the mass flow equations for reciprocating compressors, where it's clearance volume multiplied by the clearance volume to the 1 over kappa. So if you have a small clearance volume, then you get a small amount of turn down. If you have a high compression ratio, then that clearance volume has a greater impact. All right. So then here, it is just a breakdown of a fixed volume clearance pocket. It's exactly what it sounds like. It's fixed volume. It's either all the way open or all the way closed. These can be an on-off plug style, like what we see on this bell style of volume pocket. It can be on the cylinder ends, or it can be a manual pocket as well, where you unscrew the plug there, allowing the compressor to access this volume there. The main benefit of these systems is they are extremely efficient, but the downside of them is their effectiveness is highly dependent on the conditions that the compressor is running in. So then here's just some examples of what these fixed clearance pockets can look like. So here's the inside of what that bell style looks like. So it goes on a suction valve pocket, and this plug opens up and down on the compressor to access this internal volume. Here's an example of a volume pocket, and it's on a partial valve as well. And here are some unique methods to add clearance volume. These are very difficult to do. These are impossible to do while the compressor is online. You can add a spacer, which moves the valve up and away from the cylinder body, adding clearance volume within here. Some compressor OEMs design their pistons to be reversible, meaning you can change your piston half around, and then you have some clearance volume right there. And then using a head spacer is also fairly common. All right. And then this is just a cautionary note of if you are changing the bore on your compressor, you'll also be changing the clearance volume. The reason being is in all of your valve ports on your liner, there's some clearance volume in there. So if you make a thicker liner, you're adding clearance volume as well as reducing the bore here. And so you just need to factor that in and how that will impact the throughput of the compressor. All right. And then here are some examples of variable volume clearance pockets. These are the manual hand wheel style. So meaning you got to send an operator out there to adjust that piston back and forth, fine tuning the amount of clearance volume you add. Here is a hydraulic style of variable volume clearance pocket. And then here is an EVCP. So this is an electronically controlled variable volume clearance pocket. So the way these work, it has a 1.5 horsepower motor here, and hooks up to a gearbox, and then that gearbox then works on a spindle, which then moves the piston in and out. So These two systems on the right-hand side can be fully automated by the plant DCS and allow you all to have a stepless amount of gas control over a finite range of turn down. Then here are just some additional graphics for how these actually work. So they all work very similar principle to this cutaway here. It's just you're changing the mode or the method of moving this piston in and out. All right. Yeah, so for that last section, I tried to speed it up to be respectful of everyone's time. So then we'll end it with this final slide and then just ask everyone how many unloading devices they see on this compressor.
Okay, so I'm going to run a poll in a couple seconds. I'm going to give everybody a chance to check out the picture there, count up how many devices you see, and then you can get a chance to vote. And we'll do the voting really quickly because we've got 3 minutes left before we shut down. But thank you very much, everybody, for joining us. And I apologize for the inconvenient time. This is, not a very good time to be doing a webinar when everybody's trying to have dinner here. And of course, people overseas, it's going to be very late. So here is the poll. We've got options of 1, 2, 3, 4, 5, and take your pick. So if we do have any questions, we've got a couple minutes. So if you don't know how, you can expand the questions tab on your control panel, and then you can type in there and it'll send it to all of us. Okay, we're going to shut down the poll now and see what it says. So 22%, okay, 0% say there's 1, 22% say there's 2, 22% again for 3 and 4, and then lastly, 33% said there are 5. So what is the magic number?
All right. So there are 3 different types of capacity control on this particular example. So you have your variable volume clearance control, you have your on-off control or your cylinder end deactivation, and then it's kind of hard to tell, but this is on an integral compressor, so you also have speed control. For the total number of capacity control devices, you have 8 that you can see in this picture.
8,
so,
okay.
So the 3 different types, but 8 individual devices.
Yeah, okay, I apologize. Our poll didn't translate over because, again, we've only had choice for 5, and we just truncated it. So 9 is the right answer. Okay, so anyways, that concludes our presentation. But again, if there's any questions, you can ask them now, or we can always carry on a conversation on LinkedIn as well. We're gonna be available on there. So anyways, in closing, I mean, obviously recips are very complex machines, so many different options for actuation, and I think it's just important to keep them maintained, right? Keep your gas clean, and leave it to the experts to make sure that your stuff is working properly. It costs you a lot of money in downtime if they're not maintained properly and operating properly. So you got any closing words before we shut down?
So I'd just say, if you have any questions about reciprocating compressors, we are only a phone call away, and we are more than happy to help you all out.
Yeah, the guys at HOERBIGER definitely know what they're talking about, and I appreciate that presentation. That was very informational. I guess the other thing we should mention is, you guys do this kind of training, but over a longer course of several days. So, if you're interested in learning more about this type of thing, check out HOERBIGER's website. So thanks, everybody, and I hope you enjoyed that, and we'll see you on the next one in November.
Thank you very much, everyone.